Hey everyone, today we're going to talk about 2.4 inverse matrix. Hopefully this video is not going to be as long as the last one. All right, inverse matrix. So as the name suggests, inverse means opposite. So we basically try to define what is the opposite of an matrix. Now, important to understand when I say inverse matrix, it basically means multiplicative inverse because we already know what the additive inverse is going to be, and that was from um, yesterday's video where we define right here. Let me see. Property number 6, right here, that define the inverse for addition. So what we're going to try to do is now define a multiplicative inverse. So let's talk about this. Let's say given 2 square matrices. Let's say A and B. Okay. Now notice immediately that only square matrices can have an inverse because that's how we define it right now. So we have 2 square matrices, A and B. Also notice something interesting about it is that these 2 square matrices, obviously we're going to define want them to be the same dimension n by n. If this is true, if A times B is equal to identity matrix and B times A also equal to the identity matrix, then A and B are basically inverse matrices of each other. And in this case, we can say B is called A inverse. Okay, so this is how you read it. It's read as A inverse, not A to negative 1 power, but A inverse. And of course, similarly, you can say that A can be called B inverse. Okay, depending on which one you want to actually emphasize which one is the inverse. Now, with that being said, I do want you to go back to your notes and add in property number 8 about property of matrix algebra, which we didn't get to stay. We did stay 7, which is the identity matrix, that if you multiply a matrix by I, it's basically get the same thing. So here now I can add in property number 8, which say if A times A inverse would equal to the identity matrix, and that's the same thing as A inverse times A. So therefore, if you have a matrix that's square, then there is possibility for an inverse matrix that when you multiply it, it becomes the same. Now, I did say there is a possibility, and because inverse of a matrix doesn't always exist, and we'll talk about why that is the case. Now, before we move on to an example, I do want to show you how the inverse matrix work. So how about I give you a very simple example. Suppose we have matrix A, which is 1, 2, 3, 7. And let's say matrix B, which is 7, negative 2, negative 3, 1. I want you to show that they are inverses. Okay? It basically means that if you have A and A inverse, then A is inverse of A inverse, just like A inverse is the inverse of A. It's not possible for A to be inverse of, let's say, I'm going to make sure, like in this case, it's not possible for A to be inverse of B, but B is not an inverse of A. That relationship doesn't exist. So here, therefore, I'm going to try to show these 2 matrices are inverses. And how do I do that? The way to do that is to show the following. It's to show now, because matrix multiplication is not commutative, you have to show A times B is equal to I, and B times A is also equal to I. So if you do not do both ways, you actually did not show that they are inverses. It is possible for 2 matrices to multiply one way to get the identity matrix, but multiply the other way to not get an identity. And if that's the case, they are not inverses of each other. Okay, very important. Okay, just because it multiply one way to get identity matrix, it doesn't mean that the inverse have to be both directions, both multiplication. So we can definitely do this. So if I do correctly, that will be 7 minus 6 on this one. And this will be negative 2 plus 2 on this one. 21 minus 21 on this one. And then negative 6 plus 7 on this one. That come out to be 1, 0, 0, 1. There you go. If I do b times a, so we go for it. 7, negative 2, negative 3, 1. Multiplied by 1, 2, 3, 7. So therefore will be, once again, 7 minus 6. 14 minus 14, negative 3 plus 3, and then negative 6 plus 7. So that also come out to be 1, 0, 0, 1. So when you can do both multiplication and they both give you the identity matrix, then now you can conclude these two matrices are indeed inverses of each other. Now, I guess the big question is, why is the inverse so important? Well, number one, I told you before, mathematicians are paranoid. When they did something, they want to have a way to undo what they did, so that in case they screw up, they can actually undo the process and just start over again. So therefore, almost every operation that we defined so far that you've learned for the past 11 or 10 years have some kind of inverse operation to it. You have addition, you have subtraction. You have multiplication, you have division. You have square, you have square root. You have exponential, you have logarithmic. You have trigonometric, you have inverse trigonometric. So the list go on and on. So most of the operations that we define have some kind of inverse operation, provided that they are, well, one-to-one. Remember, if it's not one-to-one, we can define the inverse. One of the major usage for inverse matrix is in solving a system. So recall, if you're given a system of equation, of linear equation, it can be rewritten into matrix form, which is A vector X equal to vector B. Now, if matrix A just so happen is a square matrix and A inverse exists, then this equation A vector X equal to vector B will have a unique solution given by the following methods. Now, very important to understand this right now, is that whenever you have a linear system, as in this case in matrix form, there are three distinct possibilities for the output or for the solution set. Either no solution, infinite solution, or a unique solution. And what I just wrote define the condition for a unique solution. Okay, is that you must have, is that if you have a square matrix that have an inverse, then you will have a unique solution. So very important. Okay, now if you think about it on the flip side, that would imply that it would either have no solution or infinite solution if the matrix is not square. Okay, very interesting. So now, is that absolute condition? Is not, but that could be a good guideline when you're solving a system and try to think, oh, do I have infinite solution or not infinite solution? If your coefficient matrix is not square, very likely you're not going to get infinite solution out of that. You're not going to get unique solution out of that, because one of the conditions that need a unique solution is more or less for the coefficient matrix to be a square matrix. Now, why would have a square matrix that have an inverse would allow us to form a unique solution? Because of the following. Imagine I have this equation. Instead of go through the row operation process, what I'm going to do is multiply this entire equation by A inverse. Now, important to notice that I have to put the A inverse on the left in both the left hand side and the right hand side of the equation. Because matrix multiplication is not unique, I have to keep track of which way I'm multiplying. And notice on the left hand side, there are basically three things that get multiplied together. Associate property tell me I could multiply the first two together first, as long as I don't mess up the order of multiplication. Okay, so therefore basically what I did is I multiplied the entire equation by A inverse on the left, and so therefore I have to put A inverse on the left, on both the left side and the right side, to maintain the order. And I can now group them together to multiply A inverse and A first, and notice property number 8 tell me that gives me the identity matrix. And since the identity matrix does not change what they multiply together, that tells me that matrix A, a vector X, is equal to A inverse times B. That gives me the solution. Now, you might feel like that's kind of weird. What does that mean? Well, you actually know exactly what that means. You have been learning how to do that with algebra since, I don't know, 5th grade maybe? Imagine you have this equation. How will you solve this equation? You would multiply by the inverse of 3, which is 3 inverse, or more properly written, 1/3. And then when you have these three things multiplied together, you would group the first two to multiply together first, because associate property allow you to do that, and give you 1. And what is 1 times x? Well, just x. And now I can multiply these two things together to form the solution, which is in this case 2. That is the same exact process that we're doing, except that now we're doing not with a single variable x, but with vector x. And not with a single scalar, like in this example 3 and 6, but instead with a matrix A and a vector B. But the process is exactly the same. We're using multiplicative inverse to kind of undo the multiplication to find vector x. Now, give you a very simple example to illustrate how this works. But before I do that, do want to point out the following things. If A is a square matrix and A inverse exists, then you always have a unique solution. Okay? If A inverse does not exist, or A is not square. Now, when this A is not square, I do want to define so that A have more columns than row. If a matrix A have more rows than columns, some of the row can be trivial and be out of the system. So therefore, you can still form a square matrix. But if you have more columns than row, meaning more variable than equation, or A inverse does not exist, both of them would tell you that your system does not have a unique solution. Okay? And what's unique about homogeneous system is that if A inverse does exist, your homogeneous system has one unique solution, that is the 0 vector. So all these three properties would be come into play. So if you want to, make sure you write that down for yourself. If you missed it, just go back to the video and just replay and make sure you write it down. So if matrix A is square, A inverse exists, you have a unique solution. If A is not square because of more columns than rows, or A inverse does not exist for whatever reason, this equation does not have a unique solution. And if it's the homogeneous system and A inverse exists and A is square, then you have one unique solution, that is the 0 vector. Now, to see how this property in action, show you this example. Solve this system. by using inverse matrix. Now, some of you might already notice the problem with solving this by inverse matrix. I haven't talked to you about how to find the inverse matrix yet. Okay, so therefore you kind of stuck because this is 1, 2, 3, 7 multiplied by xy equal to 4, negative 1. But I didn't tell you how to find the inverse matrix, so how are you going to use the inverse matrix to solve this problem? Well, actually, I did tell you what the inverse matrix for this particular example is. If you look back in your notes, notice that 1, 2, 3, 7 is right here. It's matrix A. We already established that this matrix is the inverse of it. So therefore, I can go ahead and just do that. So basically what happened is this. I'm basically doing this entire process right here to show you what happens. So if I now multiply this entire equation by the inverse matrix, which is 7, negative 2, negative 3, 1, I have to multiply to the left side, which I have to maintain the order of which I'm multiplying. Meaning, since I multiply, I put this matrix on the left of the expression, I have to put it on the left of everything that I'm going to multiply. Same thing on this side. I have to put this matrix on the left of the vector 4, negative 1. Please do not put this matrix after 4, negative 1, because if you do, now your matrix multiplication is not defined. It's invalid. Now you screw up your math. If I multiply these two matrices together, these two matrices, because they're inverse, we already demonstrate that, come out to be the identity matrix. And now I can multiply these two matrices together, so that come out to be 28 plus 2. And also negative 12 minus 1. So that come out to be 30, negative 13. And what happened when you multiply 1, 0, 0, 1 to xy? You simply just get xy. So therefore, now give you the answer. In this case, the solution is 30, 13. Notice this process is a lot quicker to do instead of doing the reduced matrix method. But of course, the problem is that this rests on the fact that you can find the inverse quickly. So comes the big question. How do you find A inverse? Well, for 2 by 2 is actually pretty easy. How to find A inverse. So for 2 by 2 matrix, if A is 2 by 2, and let's say A is equal to A, B, C, D, then A inverse, there is actually a formula for that. A inverse will equal to 1 over AD minus BC, D, negative B, negative C, A. So that's the formula for finding a 2 by 2 inverse. So very simple. A strict, simple formula that allows you to actually find the inverse. So now, let's see if we can do this. You will be asked a question on your next test using this formula. So make sure you remember the formula. So how about same exact problem, solve this system. By inverse matrix. So in here, basic idea is I'm going to rewrite that in matrix form. So seem to me that matrix A in this case is 3, negative 2, 1, 4. So therefore, this is my A, this is my B, this is my C, this is my D. So now all I have to do is form the inverse. A inverse would equal to 1 over A D minus B C multiplied by D negative B, negative C, A. There you go. So now what I have to do is figure out what this number on the bottom is. So if I'm looking at this correctly, it's 12 plus 2. That's 14. So A inverse would equal to 1 over 14, 4, 2, negative 1, 3. Now I could distribute the 1 over 14 into the matrix to give a matrix A inverse, but I'm not going to do that because in this case, keeping it outside makes it easier for my next step of math. So now what I'm going to do is this. I'm going to basically multiply my equation. Oops. By A inverse. And remember, you have to maintain the order of which you multiply. Notice that these two things would cancel out. Remember, these two come out to be the identity matrix. And when you multiply the identity matrix by xy, you simply just get xy. So now all you have to do is really just multiply this thing together. So I'm going to ask you to pause your video for a little bit and then multiply them together and then see the answer that you get. If you do it correctly, I believe this is what you get. So your answer is 8 over 7 and negative 11 over 7. Negative 11 over 14. Good? Now, on to the last thing I want to show you. So hopefully we can finish this one before 30 minutes. To compensate for the one from yesterday, which was 40 minutes long, and I do apologize. But hopefully 2.5, the video would be hopefully be short. So therefore, hopefully we'll compensate for that with these 3 videos being long on 2.3, but shorter on 2.4 and 2.5. So you can kind of space it out. So now the question comes to the following. What if A is not 2 by 2? This formula allows us to find a 2 by 2 matrix, but what if A is not 2 by 2? Then we kind of have a problem. So there is a second method that allows you to form the inverse matrix. As a matter of fact, there are many different methods to form the inverse matrix. Your test will actually go for a few different ones. So this is the second one that I would like you to be able to do. So you will be asked how to do that on your test. Is that you can also find A inverse using what we call row operations or reduced matrix form. Okay? So how does it work? So the way using row operation to define inverse is the following. Is that, and this method would work for 2 by 2 matrix also. Okay, so therefore, it's also important to know. But obviously for 2 by 2, you won't use this. You would just use the formula because it's a lot easier to do. So let's say given matrix A, which is an n by n square matrix. What we're going to do is the following. We're going to put matrix A on one side. So A11, A12, dot, dot, dot to A1n, A21, A22, dot, dot, dot to A2n, all the way to AN1, AN1, AN2, dot, dot, dot to ANN. Remember, it's a square matrix, so therefore the two numbers are the same. And, actually, I don't need this. And what you're going to do is put it next to the identity matrix of the same dimension. And remember, identity matrix is also square. So therefore, this entire matrix will become like 2n or n by 2n because it now have double the number of rows. What you're going to do is the following. If you go through the row operations. So what you're going to do is apply row operations to reduce matrix A into the identity matrix. Then what happened is the identity matrix on the other side, the identity matrix I on the other side will become A inverse. So we go through this process and kind of turn this side into the identity matrix. Then on this side, it will become A inverse. What if you are unable to get A to become the identity matrix for some reason? Most likely the reason is an entire row becomes 0 on the A matrix A side. If that happens, that would tell me that A inverse does not exist for this matrix A. Okay? Now, to illustrate that process, let's do a very simple example to show you. Now, as you might suspect, I will only ask you to use this process if you are given a 3 by 3 matrix, because once again for 2 by 2 matrix you can simply just use the formula. So imagine the following. Imagine I'll give you this matrix A. Alright, let's say we're given matrix A, which is 1, 0, 0, 2, 4, 8, 1, -3, -7. So notice that I'm being particularly nice and give you the first row to be 1, 0, 0, which is exactly what the identity matrix should look like. So that should reduce the amount of work that you have to do. Find A inverse using row operations. So let's see if we can do this. So therefore what I'm going to do is basically put the matrix A next to the identity matrix. I'm going to start applying row operation to try to reduce the matrix A to the identity matrix. And whatever the identity matrix would then eventually turn into the inverse matrix. Okay? So the number of steps involved is actually the same as you would solving a system equation, which basically defined by the number of columns that you have. And in this case, hopefully it will be less. So here we go. Let's go and do this. So first I'm going to do is the following. I'm going to take row 2 plus -2 times row 1. And that become my new row 2. I'm going to take row 3. I'm going to add negative row 1. And that become my new row 3. Notice I'm using row 1 to do this because row 1 is the one that has the leading entries. That's how you usually do the row operation. So my row 1 stays the same. Row 2 becomes 0, 4, 8. And this becomes -2, 1, 0. This one becomes 0, -3, -7. And this becomes 1, 0, 1. Actually, -1, 0, 1. So notice now my column 1 is completely done. I have one leading entry, which is 1, and then now the rest of them are 0. So now the next thing I want to do is to get my second leading entry to be 1, which is the second row. So I'm going to say 1, 4, row 2. So 1, 0, 0, 1, 0, 0. The bottom row stays the same. The middle row become 1/4 of what it was. There you go. So now I get my second leading entry, which is now 1. So now I have to clean up the entire column before I move on to the third one. Remember, that's how you slowly work your way through the matrix, one column at a time from left to right. So now the next thing I'm going to do is I'm going to take row 3 plus 3 row 2, and that become my row 3 again. So row 1 is already done, so I'm going to just leave it alone. Row 2 is also done for now. I'm going to leave it alone. Row 3 is what I have to work with. So that becomes 0. That becomes 0. And let's see. 3 times row 2 plus row 3 is give you -1 on this one. Okay. And let's see what this one going to be. Will be -1 minus 3/2. So become -5/2. And this one would be 1/4 plus 3/4. Oh, nope, sorry, 0 plus 3/4, so it will be 3/4. And then this number would just be 1 because it's adding 0 to it. So notice that this one is negative. So I'm just going to go ahead and do this and just flip all the signs. Okay. Instead of write out an extra step, because that's a lot of writing numbers. And that would basically give me this to be 1. So I just have to get rid of this 0. So I'm going to go and do this. Row 1 stays the same. Row 2 is the one I'm changing. So row 2 plus -2 row 3 would be equal to my new row 2. And row 3 basically stays the same. So now this step should be my last step. Row 3 also stays the same. Okay, and now my row 2 should become this, 0, 1, 0. If I take -2 row 3 plus row 1, I get -11/2. -2 times row 3 will be positive 6/4 plus 1/4 is 7/4. And then -1 times -2 is 2. And therefore, this tells me that A inverse does exist. And A inverse is 1, 0, 0. -11/2, 7/4, 2, 5/2, -3/4, -1. All right. Unfortunately, that's all the time we got. All right. So I'll talk to you in tomorrow's video. All right. Or tomorrow's class, I guess. All right. Bye-bye.